Okay, the next thing I want to talk to you about is actually a much more controversial subject, and that has to do with global warming induced by anthropogenic activity. That is, things that man is doing, and I'm not talking about just the fact that mankind is on this planet and we breathe out carbon dioxide, and that carbon dioxide could be going up into the atmosphere and leading to global warming. That's not what I'm talking about. What I'm talking about is man's other activities, some of which may not be so necessary, where we're actually burning fossil fuels and producing carbon dioxide. So there's really not that much controversy in the scientific world as to whether or not things like carbon dioxide in fact do lead to an increase in temperature, that actually do affect or can have an effect on the Earth's temperature. What the controversy really is about is how much of an effect does it have, and how much of that effect is actually due to man's activities. So that's what I really want to talk about right now. So first of all, I want to just briefly illustrate the idea that we were talking about energetics, but basically we have a relationship between the wavelength of light, which is, if you look at light, it travels in a wave like this, and the wavelength is distance from here to here. This is what we would call wavelength. It's abbreviated with the Greek letter lambda. And we also have something else that we can measure, which is the amplitude of light, and that's how big the wave is if we measure from here to here. That just tells us how bright the light is. But what actually gives us an indication of how energetic the light is the wavelength. So this might represent a period of time, let's say, of 0.1 seconds from here to here, 0.1 seconds. And in that period of time, I actually can count the number of waves that I have, 1, 2, 3, 4. So I would say that in that period of time, I had 4 waves in a tenth of a second, or I have 40 waves per second. We just write that as 40 over second, or 40 second minus 1, that's reciprocal seconds, or 40 hertz. The abbreviation HZ is hertz. So these are all ways of saying that same thing. That's telling us the frequency of light. Well, it turns out that the smaller the wavelength, the more waves we can fit in a given period of time. And if we have a larger wavelength, let's say a wave that looks like this, now I've only got 2 waves in that same period of time. So this wave, the red wave here, has a frequency of 20 hertz. Now I'm just making these numbers up, the 20 and the 40, but it's to illustrate a point. And the point is that bigger the wavelength, the less energy that we have, and the smaller the frequency. So we have 2 relationships that we can take out of this. One is showing the energy of a wave is proportional, and the proportionality constant is something called h, which is Planck's constant, P-L-A-N-C-K apostrophe S, Planck's constant. This has a value of 6.626 times 10 to the minus 34th joule seconds. The joule is a unit of energy. If you multiply joule seconds times reciprocal seconds, you get joules, you get energy. So energy is this times frequency, nu, which is given in joule seconds. I'm sorry, which is given in reciprocal seconds. Energy is also equal to h times c, which is the velocity of light, divided by lambda, which is the wavelength. So this is telling us that energy is inversely proportional to wavelength, directly proportional to frequency. Greater the frequency, greater the energy, smaller the wavelength, greater the energy. Okay. Having said that, then I want you to understand how we can get global warming, and how it can be that radiation coming in from space is not being blocked by the same molecules that we're saying that are causing global warming. So we've got this layer up here in the stratosphere, and we've got the sun up here, and it's beating down and it's giving off radiation, and it's falling. Some of this stuff is, all this stuff is transparent. It's actually getting right through the Earth's atmosphere, and it hits the ground. This is visible light. Maybe this is light in the blue region of the spectrum, and when it bounces back up, it's going to lose some of its energy. So it's actually going to be shifted from a shorter wavelength to a longer wavelength, and the longer wavelength will be in the infrared. Some of it will be in the infrared region of the spectrum. Now, it turns out that a lot of organic molecules, and particularly these greenhouse gases, things like carbon dioxide and methane, these are a couple of the principal greenhouse gases, they all have vibrational frequencies. These bonds can get shorter and longer. These bonds can get shorter and longer. These bond angles can change. That's called bending when that happens. You can have scissoring, you can have rocking, you can have between this carbon and that and these two hydrogen atoms, you can have these two bonds shortening and lengthening in unison like this. That's called a symmetrical stretch. You can also have an asymmetrical stretch where this one gets longer and that one gets shorter, then this one gets longer and that one gets shorter. That's an asymmetrical stretch. But you have stretching and bending vibrations in the infrared region of the spectrum. When the frequency of these vibrations here matches the frequency of light, the light is actually absorbed. The infrared radiation is absorbed. It's in resonance. It's absorbed, and we actually we'll see a heating effect that occurs because of that, because the infrared radiation is a form of heat, and that actually will be absorbed by these molecules, which will then re-radiate that heat. Some of it will go into space, but some of it will be re-radiated back down to the planet. So that's the basis for the greenhouse effect. Now, it turns out that each of these gases has a different tendency to do this, and carbon dioxide is probably the worst of the three. So we've got something that are called RF values. These are radiative forcing values measured in watts per square meter. And it turns out that the values for these things is for carbon dioxide 1.66, for methane, CH4, that's 0.48, for dinitrogen monoxide, N2O, the number is 0.16. And an average number taken for chlorofluorocarbons, such as the one that I showed you before, the trifluorochloromethane, that is 0.27. And this is just giving us an idea of how good these things are at being greenhouse gases. So this has about almost four times the activity of that. This is three times as much as dinitrogen monoxide, and dinitrogen monoxide is only a tenth as good a greenhouse gas as carbon dioxide is. But you can get an idea that carbon dioxide is pretty bad, but all these gases contribute somewhat to this effect. So I don't think anybody really argues the science here. There's not much of an argument that you can make. The question is just how much warming are we getting from these gases, and how much of this is due to anthropogenic activity, and how much of it is due to just some other natural activities that mankind doesn't really have any say over. We're not affecting these at all. So that's really where the argument comes in. But there are people on both sides of this issue who have an axe to grind. There are people, for instance, there are environmentalists who want to raise a tremendous alarm here and tell us that if we don't do anything immediately, we're all going to be dead in the next 50 years. Well, many of us will be dead in the next 50 years anyway, but saying that that the Earth is kind of doomed if we don't do anything soon. And then there are other people that will say, well, that's nonsense, and the whole thing is a hoax, and there's really no effect at all from any of this activity. So, what's the truth here? What do we know? And what we know is that that we at least have to look at not popular reports that are in the media, and not reports that are issued by agencies that have some particular axe to grind. For instance, you'll see reports that come out from the American Petroleum Association or something like that. I mean, these people have it's hard for them to really be to take an attitude where they're going to say, well, we're going to investigate this without any prior bias, because it turns out that they may be some of the biggest part of the problem, and if it turns out that what they're doing is wrong, it could shut down their industry, and that could put a lot of people out of jobs and really hurt the economy. So that's not a place where we want to go for our information, and we probably don't want to go to the environmentalists, some of the more foaming at the mouth environmentalists either. But we want to look at scientific journals that are peer reviewed, where there's good and hard data, and then try to analyze that data and make some sense of that information.